Recognized for his expertise in advanced process control, debottlenecking, and large scale capex projects. His career includes key contributions such as plant commissioning at Reliance Patalganga lab facility, international capacity expansion projects, including a major formaldehyde plant expansion in Egypt, and leading waste to fuel technology initiatives at Polycycle Private Limited. Currently, Dr. Iyer serves as Professor of Practice at Thadomal Shahani Engineering College, where he bridges gap between industry and academia and bringing real world perspectives to emerging technologies such as AI driven optimization in chemical engineering. He holds PhD in chemical engineering from UDCT and is known for his strong technical leadership, consulting expertise, and commitment to operational excellence. Please join me in welcoming Dr. Ramakrishnan Iyer. Over to you, sir.
Thank you. Thank you, Mannath, for a great introduction.
Thank you, sir. My pleasure.
Before I start my presentation, I'll take a few minutes for Mann Ki Baat. Basically, we have seen almost 6 to 7 presentations in last 2 to 3 days, which covered advanced process control, that is model-based control, then soft sensors, then something about digital twin. These technologies have been there. They have been in existence for last 30 years. I've myself seen some of these technologies starting 1985. And these technologies have been developed extensively, implemented worldwide. Of course, in India, these technologies are not implemented, have not been used much because Indian scale of operation is low compared to the scale of operation worldwide. So my confusion is whether we can call these technologies as AI, whether they are AI in the context of current AI, which we are talking about. The current AI is basically on using LLMs, large language models, which are either they can be used independently as standalone, or they are used with wrappers, typically like NA10 or Crew AI. And they are also integrated with RAG, where we can integrate our knowledge with the huge, humongous knowledge of LLMs. So we as a chemical engineer or as chemical engineers, we have tremendous opportunity to use this system, which has disrupted the workspace in last 4 to 5 years. And there is a tremendous opportunity for us here. So what is that opportunity? The opportunity is that we should work with this huge brain, which is available to develop agents, agentic AIs, which could be used for design, engineering, and operational excellence in chemical industry. So what is the incentive? So this kind of AI which we are talking about, or this agentic AI, is really very expensive. Currently, it is available only at a low price. That is only carrot. And it will be, it is funded, basically these companies are funded by venture capital companies, which sooner or later, they are going to extract pound of flesh. And when that happens, there will be a transition from a low price, low tariff system to a high tariff system. Typically, like we had Geo, Geo was free for 1 year. And subsequently, you see the price of Geo, is almost at par with other companies. So similarly, the price of AI is going to be fairly high, and it will be difficult for Indian companies to use this. The second reason is that the engineers from core engineering faculties, core engineering, typically like chemical engineering, mechanical engineering, electrical engineering, civil engineering, they are all very low paid, glorified, fourth class people. This is the situation today. I am really ashamed to see, because when I joined chemical engineering in 1975 at the ICT, UDCT, it was #1 branch. And almost top 30 students of Bombay University, they used to join chemical engineering. But today, most of the colleges, they are closing down chemical engineering. The reason, because the students, they find a large gap between their salary level at the entry level, between them and the salary level of computer engineers. Some of these chemical companies, they offer very low salaries. So this has to change. And this AI, which we are talking about currently, this Gen AI is a great opportunity to change this. We can change this landscape by combining our knowledge of chemical engineering or knowledge of core engineering with AI and developing AI agents, which can then become a and where the Western world can become the marketplace. India cannot be a marketplace for these AI agents because the cost, engineering cost of engineer is fairly low in India, while cost of engineer in United States is almost 30 to 40 times. And therefore, only Western world can afford to replace the engineers with AI, while in India it may not be viable. Another very important observation is that now, luckily, we have President Trump, who is against immigration, and he has put a high penalty on H-1B visa. This is where we have a great opportunity. And this opportunity must be used by EPC, EPCM companies, and they must utilize all these engineers from core branches to develop AI agents, which can then be sold or which can be made available as SaaS, what is called SaaS, that is software as service. And that can have really great margin, while this current EPC margins are fairly low. So they can have a parallel pipeline of SaaS where they can combine their experience, their knowledge, which they have developed over a period of last 30, 40 years, and they can combine this along with the knowledge embedded in LLMs and develop AI agents, which could be used by Western world. So with this, I think we need to give a thought, and our students particularly, they should start training themselves on this LLMs, and they should also train themselves on the wrappers. These are wrappers typically like N8N or like Crew AI. They should start training themselves, and they may attend even some courses related to these AI development, in order to combine chemical engineering with AI, so that their value will be much higher, will exponentially increase in chemical industry market. So with this just little man ki baat, I will start my presentation. My presentation is going to be on dynamic predictive modeling. Again, I'll emphasize again that this is also not AI. This is purely modeling, which is used for control of the process, where we can use it for predictive analytics or developing soft sensors or use for advanced process control. This also we cannot classify as AI because the current AI is basically based on LLMs. Of course, we can use these models, we can combine them with LLM and build a AI system which can be extremely useful. Now, dynamic predictive modeling, I had an opportunity to work with a Canadian company named Triber Control. And this idea of using time series analysis for modeling the dynamic behavior of plants was mooted by Dr. Steve Triber at the time. And of course, Triber Control has been acquired by Aspen. So now this company is not there anymore. But the whole idea of using time series analysis for dynamic predictive control is extremely useful. And that is the reason I thought that I can make a presentation on that. So the agenda for this presentation is that I'll give a brief introduction about this dynamic modeling system. Then I'll explain this time series analysis, which is basically pioneered by Box and Jenkins. And Box and Jenkins method is even very, very relevant today. Then we will go to case study where I will explain, take the quality data modeling, and I'll just give you an overview. My entire presentation is only an overview. It is not a training program. One needs almost a week's time to get trained on this time series analysis. So this lecture is only an overview. Then I will explain the application of this system, that is Box and Jenkins method for model identification of plant data. This model then is metrics based model is then used for developing predictive control, which is also known as advanced process control. So we will see another case study where there is a model identification for an extractive distillation system, and how this model is predicted using how model prediction is done with Box and Jenkins method. What is time series? Because we have a lot of students here, so I thought that I should include this slide, and those practicing engineers may know what is time series. Time series is a collection of data. A plant,
Sorry
normally
to
you
interrupt,
have.
sir. Sir, actually, the slides are not visible.
Okay,
They are
okay.
not moving.
1 minute, madam.
Yeah.
Slide move with me. Now check, madam.
Yeah, slide is visible, but it is not moving.
No,
Yeah,
no,
now
it
we
is.
can see. Yeah, now
Oh.
it is there.
Okay,
Yeah.
okay.
Yeah,
Okay.
thank you.
Slide show. Okay, okay. There's a problem with slideshow. That is the reason I think this happened. Anyway, so basically time series is a collection of data at a certain frequency of time. Normally, when you see plant data, it is mostly collected every minute. Although the scan time of the instrument may be in microseconds or nanoseconds, even these days it could be nanoseconds, but the data is collected over 1 minute interval, and you can see that there will be large amount of data that will come when you collect for temperature, pressure, flow for the whole plant with almost 40 to 50 parameters. And they are ordered in the sense that they're sequenced. They are indexed over time because they are with time they are collected. So it is an indexation. Time becomes the indexation, and because they are collected at regular intervals. The idea of collecting this data is to track changes. So this is called historic data of the plant, so that we track the changes. Many times we say the plant is under steady state, but steady state doesn't mean that the difference between the current value and the previous value is zero. It's not like that, because there is some variation, and the variation can be affected because of change in the feedstock quality, change in the feed flow. There are some changes in the control systems. So changes may due to operators, changes due to external conditions, typically like temperatures, ambient temperatures, like day temperature could be some 30 degrees, while night temperature could be 10 degrees. And that can affect the working of exchangers, especially air coolers. It can affect the working of blowers. And therefore, therefore, there will be some variation in various parameters like temperature, pressure, and so on. So the whole idea is of time series analysis is to forecast the future. Typically, this is used in forecasting stock prices. And it is also used in weather forecasting. It is also used in forecasting website traffic. It is used in forecasting airlines traffic, so on and so forth. But we are going to be focusing only on chemical industry data. The key feature, as I said, it is a chronological order. That means the sequence matters. We cannot take data from anywhere and use that. It's a temporal dependency. Temporal dependency means time dependent, because the past data influences the future observation, and therefore we have to take this data in sequence. That is why we said we call it time series. Now, typically, I have just displayed one plant data from a plant. This is a plant, a formaldehyde plant, where we have temperature, pressure, flow rate, vibration level of pumps, valve positions, motor speeds, so on and so forth. This is a very small data set, and data set could be very large. So you can see that it's a sequential data set in time. So there is a timestamp. So we are collecting the data here. This is a time series. So we are collecting the data with time indexing, which could be used in building the model. So what is the whole objective? The objective of this whole thing, we can see that there is a huge amount of data that is collected by the plant. Many plants in India, they dump this data on some hard disk and they never use it. But this data has a lot of information. It's the knowledge of the plant which is embedded into this data. Some plants, of course, refineries like Reliance Refinery, Reliance Petrochemical Plant, they all use this data. They collect this data in a very systematic way through real-time database like InfoPlus of AspenTech or PhD of Honeywell. So on this DCS, they collect this data and they systematically utilize for designing the advanced control systems. The whole objective of collecting this dynamic data is to leverage this information which is embedded in this historical data to forecast the future behavior. Why should we forecast the future behavior? This is typically what is required for advanced process control. When we are controlling a plant, we have to see whether the plant will start drifting at some other point. Then we need to use the controller to bring the plant back to its base level. The advantage of advanced control is that it significantly reduces the variation in parameters. By reducing the variation in parameters, we can operate the plant close to the constraint. And this could mean a profit benefit of close to 5 to 10%. Some places it could be 10%. Some places, a well-managed or well-operated plant, the benefit could be 5% in terms of bottom line. So the payback periods are in less than months, few months, maybe a couple of months, because the cost of advanced control is not really very high. So with large-scale plants, the advanced control has a very, very good, very low payback, means good payback in terms of few days. Applications are also in soft sensors. Soft sensors were discussed by our Dr. Path earlier presentation, where he talked about soft sensors, using soft sensor for quality prediction. It can be extremely useful. This dynamic modeling can be very useful for fault detection. When we say that we are collecting the data, we assume that almost all the instruments, they are giving correct reading, which is not true. Almost, I can tell you, 20 to 30% instruments, they sometimes give wrong readings. Wrong reading because of non-calibration, wrong reading because of the drift, and there are many other reasons where you could end up in wrong reading. And if you do a proper prediction, you can check the instrument and bring it back into its normal state and therefore avoid some abnormal situation. It is also used in real-time optimization. It is used extensively in model predictive control. The whole purpose of this time series analysis and my presentation is application of this in model predictive control. So what are the challenges in modeling this data? The most important challenge that this data is non-linear. It's not a linear data. If it is linear, I can easily fit a linear regression and then use this data linear regression model for my control or prediction purpose. But it is a non-linear data, so simple linear regression is not going to work. Can we use some non-linear regression? That also is extremely difficult because we don't know what kind of non-linearity the data has. So it is linear regression or a non-linear regression will be insufficient for accurate prediction of the future data points. There are time delays. There is a transport lag. If you see when you have a pipeline, you have some residence time in the pipeline. And therefore there is a transport lag. This lag could be even a minute or 2 minutes. And there are residence time in reactors, residence time in heat exchangers. So all this could lead to delay in the process data or process indication. And therefore, the prediction has to be done in a different way. And thirdly, there are multivariable interactions. For example, we change the reflux ratio or we change the reflux rate in a distillation column. Immediately there has to be some change in the bottom boiler. We have to change the bottom boiler. Otherwise, we'll end up in high value product in the bottom. So these two are closely related. Similarly, there are other parameters which may be closely related like feed, condition of the feed. So all these parameters can lead to multivariable interaction and strong coupling of these variables, which complicate the model building using normal machine learning methods. So we need to understand the data. Data has a lot of information. Data wants to tell you a lot of things, but we are not ready to listen. That is the main problem. So if we are going to listen to the data, then we can operate the plant very close to its constraint level. So there are two types of data. One is a high frequency data like DCS or PLC systems. They record process variables every minute, every second, and sometimes there is a scan time of even nanoseconds. That means we are not recording the data, but that the transmitter is getting the data at nanoseconds. But we are recording the data in seconds or minutes. So these are called high frequency data. Then there is another data, which is the lab data, or even online analyzer data, which is a low frequency data, because this data comes at a frequency of maybe half an hour, 1 hour, or even shifts, one shift, or even days. So this is a low frequency data. So we have a mix of data, which is high frequency and low frequency, and we have to build a correlation using both these two types of different frequency data and use this correlation to build control. There is a difference between simulator and control model. Control is working online, so it's extremely critical. If your controller is not accurate, and if your advanced control system is not accurate, it can lead to runaway, it can lead to explosion, it can lead to fire. So these are some of the risks associated with advanced control, and therefore the data and model building has to be extremely good. Now, when it comes to time series, there are two terms. One is called stationary time series. The other is called non-stationary time series. What is a non-stationary? Stationary time series where we have a variation in data, but it's a random variation. There is no fixed trend. So that data is called stationary data, where the mean and standard deviation remains constant. While a non-stationary data is the data which keeps shifting. It can shift due to operation mode. It can shift due to external disturbances, typically like day-night temperature difference or difference in summer and winter temperature difference. So the data could shift, and therefore we need to have a different approach for non-stationary data. Now, as I said, the data quality is extremely important before building the model. Before building the model, we check the data thoroughly, and we have several techniques to check the data quality online. And there are some real world data will have some missing values, some outliers, sensor drift, then some data which will say NA. If you have worked on a machine building exercise, you will see that the data will have many places there will be some NAN. So because there is no data there. So we've got to remove all these values before we start modeling. So we need to, the most important other point is that we have to understand the data, the characteristic of data. Otherwise, we will end up in misleading model, and model in a process control system has to be very robust. When you are doing an offline simulation, it's not very important that it has to be very robust. You can play around with the model and arrive at some values which are close by. While in case of process control, it has to be very robust in the sense that the values cannot be too different. You cannot have different values at different times. You cannot send different signals to the controller at different times. And therefore, the modeling is extremely important step. So what is the problem here? What is the problem we are addressing here? We are addressing a situation where we need to build a model. We have to build a model that will predict based on the history of the data and the past measurements and the current measurements, and we have to build a model. So typical use cases: predicting quality, developing soft sensors, and forecasting the process trajectories for model predictive control. Now starts the mathematical work. So a dynamic relationship in case of time series modeling. It typically looks like this, that you have the current value is a function of previous values. That is yt, t is the current time, is a function of previous time, one time previous, second time, third, like this, three different steps, all the previous steps of the data and previous values of the input. So we are trying to build a function using this. A function could be a linear function or a non-linear function. So using the current value, and we are using the current value and the past values. Our objective is to predict the future value. Now, these are the terms which are commonly used in time series modeling. The first term is autoregressive model. That means the model or the procedure automatically carries out regression using the past data. It may use the current data, it may use immediately past data, or it may use 2 steps past data, 3 steps, 4 steps, 5 steps, depends on the goodness of fit. If the fit is not good, it may have to use 2 to 3 steps. That model is called AR model. Now, another model is where it is RMX, which uses the noise term. What is the noise term? The data which we generate is not always smooth. We are not generating data using some mathematical equation. We are generating data from the transmitter, from a temperature indicator. So this is never a smooth data. And therefore, there will be, when we fit the data, we extract all the information from the data. The balance information is the noise. What is meant by this? Suppose I have a linear model. Let's say I fit a model y is equal to mx plus c. This may use all the information that is available in data. But if you calculate the difference between actual y, that means this is only y fitted, y model and y actual. If you calculate the square and sum up the squares of this and take an average, you will find that this is a finite value. That means our model is not exactly fitting the observed data. So our model is not exactly fitting the observed data. The rest of what happens to rest of them? So the rest of the data could be noise. Rest of the data is something which we are missing. We are not able to fit properly. But there is also a noise term, which is the difference between the y actual and y estimated. The difference between these two is the noise term. So using the noise term and moving average of the noise term, we can predict the future data. These two are statistical methods. There are two methods of modeling in chemical engineering. One is called deterministic method. The other is a stochastic method. Stochastic method uses statistical techniques, while deterministic models are based on equations. So state space model is one such equation which uses differential equations for the variables and uses these differential equations to solve the multivariable problem. Any questions? So I assume there are no questions.
Hello, sir.
Yes, go ahead.
For modeling, we have to use partial differential equations for number of variables.
Hey, I'll tell you, when we are talking about process control, it's a very
Okay.
simple principle. Is that
Okay.
keep it simple, stupid. KISS principle. You should always try to keep your model very simple. The reason is we are talking actions in seconds. So when you're going to take action in seconds and you spend minutes in calculating it, it's not going to work. It's not going to give you proper control. So we try to keep the model very simple. So using partial differential equation or large differential equations could be really detrimental to control system. So mostly we try to use, in case of state space model, we use only ordinary differential equation, and that too maybe up to second level, first degree or second degree at the most. And solving partial differential equations analytically is going to be an extremely difficult task. And numerically, when you try to solve them, you may take few minutes. And we don't have so much time in process control.
Thank you, sir.
Okay, thank you. So machine learning methods also have been used in model building. But many of these machine learning methods, as I told you, they are time consuming and therefore they cannot be used for process control, but they can be used for predictive analytics, typically like SVM, like support vector machine, which is also known as support vector regression, like random forest, which is basically based on decision tree analysis, and gradient boosting, which is based on the numerical difference, which you use the numerical difference between the first value and second value and calculate a numerical derivative and try to move along the gradient. So these are some of the machine learning methods which are used. So we are not going to talk about them because we are not using them in this case. And also there are neural networks. These models are very complex, as you know, neural network. People have talked about neural network. But neural network models, they are used in LLMs. LLMs, of course, use neural network models for the large amount of data for prediction of the future values, but they cannot be used in process control. This is just a summary that the most important advantage of the requirement also or advantage of dynamic modeling is that it is a proactive operation. That means before the plant starts shifting, you are controlling the plant back to its base level. And how is that possible? That is through dynamic predictive modeling. The predictive word itself says that we are going to predict where the plant is going to be in the next minute or next few minutes. And then we start taking action so that plant doesn't move to that position, plant doesn't drift to that position. And therefore, we minimize the oscillation in the plant, minimize the variation in parameters, and therefore we are able to extract the benefit out of this steady state approach, steady state of the parameters. As I said, that we need the success of modeling is based on how well you know your data, how well you know what is noise, how well you know what is the delay in the process data, and you account for all this in your model, then you can really build a very successful predictive control system. Now we get into some details of this time series analysis. And this method is called Box and Jenkins method. Box and Jenkins were the scientists who developed this method in 1970. Mathematicians, they were statisticians. And this Box and Jenkins method is used even today. It is extensively used in predictive analytics, especially where the data is in time series form. So what is the method? The concept is to understand the properties of this time series data using statistical techniques. You use statistical methods to understand the variation in the time series and how you can account for that variation into building the predictive model. So you need to break down the data into three parts. One is the trend. So there is a trend in the model. There may be a trend in the data. Then there may be seasonality in the data. Seasonality means, again, as I said, day and night. Your day temperatures could be much higher than your night temperature. Typically, in some places, the night temperatures, especially in North India, could be 3 degrees, 2 degrees, while day temperature could be 20 degrees, 22 degrees. So such a vast difference between day and night temperature can significantly affect the performance of the plant. So you need to understand this variation, the seasonality of the data, seasonality in terms of winter, summer, or seasonality in terms of if there is monsoon in that area. So what happens to the data when there is a seasonal change? Seasonality change need not be the season change alone. It can be change in the data due to some variation. And you need to know noise component. Noise components are, as I said, that if you're not able to estimate the noise component, you may not extract everything out of data. Data may have 100, let's say units of 100 information. You may be able to extract only 60% of that information. And you may think 40% is noise, but that is not true. The noise could be only 10%. Noise means the data which cannot be predicted with the model. So we need a good model will take care of this entire data value, the value in the data, extract the entire data value from the data using right methods. And that is where we have a box thinking method, which is called ARIMA method. Now I'll explain these terms. So as I said that we are decomposing the data into three parts: seasonality, we have noise, and we have trends. We will try to even smooth the data with the help of what is called moving average. Moving average is basically you go on collecting the average of past data, maybe past 4 data, past 3 data, and keep changing. The data will keep changing, and therefore the average will keep changing, and therefore this average is called moving average. There are other exponential smoothing methods. Right here, I'm not discussing those methods because there is the details can be discussed separately. And of course, Box and Jenkins method. Box and Jenkins method has been extremely useful, and it's an iterative approach. It has been remarkably successful. It's used by share market predictors. All these companies to predict share market price, share price of a particular stock. They use this time series Box-Jenkins methods. You can see how useful. I mean, in terms of money, of course, it's extremely useful. Data driven because it uses the data. It doesn't depend on some equation or some mass transfer equation or a heat transfer equation or momentum transfer equation or some model rate equation. It doesn't depend on that. It uses the data, the information inherent in the data, and it uses this inherent information and converts that into knowledge, which can be used then to control the plant. There are some drawbacks of this system. If there is too much change in the plant parameters, you cannot use this method. We are assuming that plant is close to steady state. Plant is always steady state for an observer who is looking from far, but who is looking very closely, who is looking the plant very closely. For him, it is not a truly steady state. That means the values are not constant throughout. So although it's called steady state, but there are some variations. If there are no variations, there is no need to do dynamic modeling. There is no need to do this modeling, or there is no need for advanced process control. Because there is variation, there is advanced process control. Now, as I said, that ARIMA is basically an autocorrelation model developed by Box and Jenkins way back in 1970, and it is extremely useful even today. So there are three parts to this ARIMA. One is autoregressive. That means it takes the data and carries out regression based off the past values to predict the future value. So it is autoregressive. The second is the moving average. That means you take the moving average of all the error values. So when you have an autoregressive model, there is some error, may not be able to predict everything. So you carry out a moving average of the forecast errors and use that moving average to calculate the future value. And the third is integration. What is meant by integration is really we are differencing. When we have a trend in the model, that means when the data is not stationary, that means the variation is not random, but there is a steady increase in the value or steady decrease in the value. We say that it is a non-stationary model data. So when you carry out difference, the non-stationary attribute may disappear. The non-stationary attribute of the data may disappear, and then it can become stationary. Sometimes you may have to take one difference may not be enough. You may have to take two difference. That means you first take the first difference, then again take difference of the difference. Then probably the data will become stationary. And the first and the foremost condition of Box and Jenkins method is that the data has to be stationary. You cannot work with a non-stationary data. You cannot work with a time series which is non-stationary in nature, because the principle of ARIMA doesn't work on non-stationary information. It has to be typically a stationary time series. So you can convert this non-stationary time series into stationary time series by differencing. That means you take the difference between two data points. Like this, you take the difference of all the data points with the adjacent data point and plot that difference, then it may become stationary. If it doesn't become stationary, try the second level. Now, normally you don't go beyond two derivatives. It is a derivative, basically. So you don't go beyond two derivatives. Then you discard that you can't use this method. Typically, you can see the characteristic of non-stationary data. One, you can see a visible trend, upward trend or downward trend in the data. There is a seasonality. That means it keeps repeating. The data keeps repeating after a certain, that means it has a periodicity. It has a periodicity that it keeps repeating after certain period of time. And the variance in the data keeps changing. That is a calculation. You can do a calculation of the variance, and the variance keeps changing with time. So these are the three indications of non-stationary data. Then there are two methods which are used commonly for this autoregression. One is called ACF, and the other is partial autocorrelation, called PACF. Now, ACF is basically you are correlating the data in the time series with the past values. It's a very simple principle that you're going to correlate the data with the past data. So it's like data memory. The data is having some memory. That means it is the data inherent within the data is about the process. It is having some memory, and you are trying to capture that memory with the help of autocorrelation. Now, when you have autoregressive model, there is a parameter called P. It is indicated as P. What does it mean, P? P means how many steps in the past, the data from how many steps in the past you have used to predict this model. When we say predict, make this model, what we mean is that we should at least cover 80 to 90%. We should capture at least 80 to 90% of information within the data. That means our right-hand term, excluding the error term, that is excluding the epsilon term, this term should capture at least 80 to 90 or 90% of the value which is there in y term, actual y term. Then we say that we have captured the data enough, and it could be the epsilon term could be a white noise. Otherwise, our data fitting is not good. Now, suppose, so we go back to one level, we go back to second level, we collect the data from the previous two levels, we collect the data from previous three levels, then it becomes third order model. If we collect data from two levels, previous two levels, it is a second order model. Then P is equal to 2. And if we collect data only, we require data only from first level, then P is equal to 1. If that is good enough to predict the capture all the value, then P becomes a first order model. The second part of this ARIMA is the moving average model. So we take the error out of the prediction, which we did using ACF. We take the error and we plot the error. And we take this error as a linear combination. We plot this error and we fit a model. We take the moving average of this. So here also this Q factor is basically how much of past data you are going to use for collecting the moving average. So the moving average we normally collect with one or two values. We don't collect with many values. So Q is normally 1 or 2, or sometimes it is even 0. Many times you may not need, if your first autoregression model is good enough to. So combining these three things. The third part is the integration model, integration. That means if the data, time series data is not stationary, that means there is a variation in mean and variation in standard deviation, then we need to make the data stationary. How do you make the data stationary? As I explained, by taking difference. So how many differences you are taking? Let's say you're taking one difference, you're taking two difference, or you're taking three difference, then the value of Q will be 1, 2, or 3. So we have now in ARIMA three parameters, P, D, and Q, and they become the model parameters to predict the future value. So using the past data, we have to estimate these three values, P, Q, and this, and based on that, we can build a model which is this, which can be then used to predict the future values. There is another method called SERIMA, which is a seasonal ARIMA, where if you find that by differencing you are not able to convert this seasonal ARIMA back into a normal time series, a stationary time series, then we use what is called SERIMA. It's a very complex model, and normally we try to avoid using this SERIMA model. There is a nice book by Box and Jenkins. If you want details of these methods, you can go through that book, and this modeling will be extremely useful in future. This modeling procedure will be extremely useful in future, especially for predicting the plant data. So there are three parts. We have stationarity. That means we establish that the data is stationary. There is no seasonality. We apply the transformation to make it stationary. Then identification using ACF technique, and then estimation of the parameters. That estimation of parameter is based on least square technique. You must have heard of least square technique for estimating a regression parameter. This also uses least square technique, and this technique is called maximum likelihood technique. So you calculate the max residuals and minimize the residuals, and have high correlation coefficient, which was explained by Dr. in the earlier presentation. Now comes the part, how good is our model? We may make a model, but we don't know how good that model is. So there are two methods. There are two parameters which are used to see goodness of fit. These parameters work on the principle that the model should not be very complex. That is very important. You should not use too many parameters in the model, or too many of these past values. And second, what is the error that is there in the model? And these two parameters are called AIC and BIC. AIC is in the name of a Japanese scientist, IKK, who devised this model, where he put a penalty function. If you are using too many parameters, then you have a penalty function. You can see plus 2k. And likelihood is basically the goodness of fit. How good is that fit? That is called likelihood. So it's a combination of likelihood and the number of parameters, complexity of the model. If the model is too complex, AIC will be high, and high AIC means your model is not good enough. If AIC is low, the model is good for use and you can use the model. The second method is known as BIC, which is a Bayesian probability method. And it is also based on statistics, but it puts more penalty. The penalty is much more if you are using too many parameters. If you use less parameters, the penalty is less. So modeling is a balanced, it's like balancing on the rope. You cannot have a very complex model and you cannot have very simple model. If it is a very simple model, it is underfitting. If it is a too complex model, it is overfitting. And both of them are undesirable for process control. So you need to have a very balanced model, minimum number of parameters with maximum value extraction out of the data. So it's a tricky exercise, requires some experience apart from the mathematics itself. So here there is a case study where a soft sensor has been built using this quality data modeling. I am going to briefly run through this. So it's basically, again, as I said, it's an iterative cycle. You have identification, estimation, and diagnostic. And so differencing to remove the trend. So there was some trend in the data. So a differencing system was used to remove the trend. This is from a chemical process where we had the quality data. And this is typically the graph of the quality data. Now we need to predict the future. We need to build a model that will predict the data. So it's called, that is what is basically soft sensor. Soft sensor is the term used for a predicting model, a model that predicts the quality data. Basically, again, using ACF, residuals, and you have a final forecast, which is plotted here. You can see this is the outcome of that model. And this is another example where CO2 level in a city is monitored. The CO2 level varies. It is values are different for different years. It is plotted against year, and this is not a stationary model. So because there is a strong seasonality in this model based on year to year, and therefore you actually reduce the model, you use what is called SARIMA. That means you consider 12-year seasonality separately and multiply the ARIMA model with the SARIMA model in order to predict the values. It's a complex model and normally not used for process control purpose in laboratories. This CO2 modeling, which was done, is an imperfect fit. It was not a good fit. So really, we are not essentially looking for a good fit all the time, especially which are offline models, which are not going to be used for process control. We are only looking for a trend so that we can take corrective action based on the trend of the model. So this is a kind of summary which says that the power of method is not in a single answer. It only provides a framework for the analyst to apply their expertise. And this has to be practiced, redone, recycled. We should collect more data points in order to improve the predictability of the model. Another important application of this process is in model identification for process control, which we talked about advanced process control. And this is where it was used by Triber Control, and I had worked along with him in India. I represented Triber Control in India. That is where he trained me on building time series models for process control. What is extremely important, bedrock of process model, what is extremely important for a process model, that it should be a high fidelity model. That means the model should be stable. It should not be oscillating too much. It should not be oscillating. Its dynamic behavior should be very stable, and therefore we need to build a model which will extract all the data, but at the same time, it should not be too complex. So when it is not complex, when it becomes a simple model, then it becomes a robust model because it's easier to calculate and it is easier to control the process. The second purpose of this model is improving the overall efficiency and product quality. There is a term called quality giveaway. I don't know how many people have heard this term, quality giveaway, which is an important aspect in process control. Let us say we have a distillation column and I have customers who ask me for 98.5% purity of the product in the top. Let's say benzene. We are producing, separating benzene and toluene, and benzene purity we want 98.5. The customer says he wants 98.5. But you try to be a little over smart, an operator, and he says that he produces 99.5% quality. Is it a good thinking or a bad thinking? It's not, I mean, it is not a good thinking because customer is not going to pay you extra for that difference. He's not going to pay you because you are supplying a 99.5% purity benzene, while he wants only 98.5% purity. This is known as quality giveaway. This is, and in doing this, we will be having more reflux. More reflux means more energy in the reboiler. So we are spending more to give him something which is not required for him, which is not asking for it, but we are trying to give it by spending more money, and we are losing the profit inherent in our material. So this quality giveaway can be avoided with the help of advanced control. And why operators tend to do this? There is a psychology in the operator. Operator tries to be super safe. He wants to be super safe. So he tries to keep away from the specification in such a way that he feels that if there is a problem, at least he will reach close to the specification. The reason is that he doesn't have very close control on the plant. While an advanced control system can maintain a very close control by monitoring the plant every minute using some of these dynamic models and therefore maintain the plant close to the specification without quality giveaway. So quality giveaway is a very important aspect in advanced process control. So if you want to reach very close to that product quality, you need to have a very good model. Now, traditional, even today, it is being used, although I'm calling it traditional, it is a traditional step. If you see advanced control steps, you'll find the first step is to identify the model. First is you carry out a process analysis, you study the process thoroughly and find out what are the controlled variables, what are the manipulated variables, which control variables are affected by which manipulated variable, what is the interaction or coupling between various variables, because one control variable may be affected by several manipulated variables. So you identify all this by studying the process very closely. One has to sit with the operator and see how he's operating and what are the variables, how he makes changes in order to achieve steady state. So first step is to achieve steady state, bring the plant to steady state, then make a step change. Let me see, suppose we want to relate reflux quality of the top product with reflux rate. So reflux rate is a manipulated variable and quality of the top product, which let us say we have online analyzer and we are able to see the quality of benzene, for example, in benzene and toluene system. So reflux rate is the manipulated variable and quality, that is that 98.5%, that quality of top product is our controlled variable. So we make a step change, we make a change in reflux. And then we study how we carry out, we plot the graph of the quality versus time. we make a step change, means let us say I change the reflux ratio by 10%. And then I will see what happens to the quality. Now you will ask me why 10%? Why not 1%? Why 10%? If you don't make a major step change, you're not going to see any real change in the quality. You may see a change into first decimal or second decimal place. So that you don't know whether it's a noise or it is real change in the quality. So you may not be able to build the model. So if you want to build a model in this, you may have to make a significant step change in the manipulated variable in order to arrive in significant change in the control variable. What does it mean? The plant will come to a new equilibrium. What has happened here? That you have disturbed the plant. So plant gets disturbed here because of the step response method. So what is the cost of this simplistic approach? This is a simplistic approach of getting the model, dynamic model out of the plant. It can lead to upsets. You make a small change and you leave it to the operator after, let's say, an hour, you collect the data for 1 hour and ask the operator to go back. It may take a lot of time for him to come back to that level where the concentration is 98.5. So you have disturbed the plant, you have produced an offset product for a long time, for almost an hour, and subsequent to that also when the operator takes some time, may take an hour or so to come back to that 98.5% value. So you have lost that time. You have produced an off-spec product which needs to be recycled and reprocessed to get back on-spec product. So you are creating a disturbance to the plant. You are leading to instability in the plant. So economic impact is there is a disruption in the plant and wasteful recycling of the material. So what Dr. Steve Treiber, he came out with a different technique. He said, when we are doing a test in the plant, it's a live plant. In the live plant, when we are doing a test, we should not disturb the plant too much. So we disturb the plant to a level that we get the information. At the same time, we are able to come back to the original state very quickly. And to which he devised a pulse type of response technique, and that is called PRBS. Step input, as I said, is this test is known as pseudo-random binary sequence. Pseudo-random binary sequence. What it means? You select a random sequence, but you don't disturb the plant too much. You disturb it by, let's say, 1%. That means you change the reflux rate by, let's say, 1 or 2%. You take the reflux rate up by 1%. Then again come back to original state. Then keep constant, remain 0. That means don't change the reflux. Let it come to equilibrium. Again disturb it. That means go back to higher reflux. And then again keep it for a minute. And so it kind of a repeating binary states. That means you have only 2 states, that is +1 and -1 state. Now +1 state could be 2% of the value and -1 again could be 2% of the value. So you are not letting the plant know that it is getting disturbed. Somebody is disturbing it. Plant will not come to know, because as soon as it is disturbed, you are coming back to original value. So the plant does not have enough time to get disturbed. And this randomness of the event will keep the plant under steady state. So you get a sequence of information using this PRBS test. And this sequence of information then can be used in what is called ARIMA model to build the dynamic model. Now this is a stationary model, the series, because you are increasing and decreasing randomly. So there is no trend for the data. There is no, this is a stationary data. So there is no seasonality in the data. So this stationary data can be nicely used to extract the model out of the data using. Then there is a technique called cross correlation coefficient. You try to get cross correlation coefficient from the data, and that there are some equations which are used to build the model. Now, those who have studied process control, they must have heard of Laplace transform model. In process control, we use Laplace transform models. These Laplace transform models are derived using step tests. So when you do a step test and you get the data, then you know how to convert that into Laplace transform model. You know that you take the slope of the curve, and from the slope of the curve, you can get the time, response time, and the starting point will give you what is the dead time. So you develop a Laplace transform model e raised to minus tau s divided by tau 1s plus 1, which is a first order model. Most of the models are in the first order. Very rarely we use second order model in advanced process control. Now, so you can see that time series analysis does not disrupt the operation. So operators are very comfortable in testing. Testing is one of the main activities which takes a lot of time. If I have an advanced control project which may run into 1 year, I spend almost 6 to 7 months in testing the plant. The reason, the operators, they are averse. They won't allow you to change. They are averse to this change because they are responsible ultimately, or they are accountable for any disturbance in the plant. So if you tell them, no, I'm not going to disturb the plant, I am using PRBS method, which will keep plant always at the steady state, then they are open. They are open to testing, and therefore you are able to collect the data very quickly, maybe within a month or 2 months. While step test, if you use a step test, it may take you 6 to 7 months for the operators to come around and allow you to test the plant. So as I said, that if you're not disturbing the plant, you maintain the product quality and there are no upsets. There will not be any upsets in the plant. And the model which is extracted using this is a statistical method, and it builds a very robust, simple model. So this is a comparison, head-to-head comparison of the step response method and time series analysis using PRBS. Weber Control started this method long back, sometimes in 1993, 94. And now there are a lot of agencies which use this PRBS method in order to test and extract the model from the plant. So we'll see an example of this modeling dynamics of plant for a complex distillation process. This example I have taken from a published paper. And this is the idea is to tell you how the modeling is used for developing, how this time series analysis is used for developing a dynamic model to be used for advanced process control. Now, the challenge in this particular problem is that it is a separation of methyl cyclohexane and toluene. They are very close boiling, and therefore it is very difficult to separate them by conventional single distillation column. So here an extractive distillation is used in order to separate methyl cyclohexane and toluene. Their boiling points are very close, although not too close, almost 9 degrees. If you see ethyl benzene and styrene, the difference is only 2 degrees. So in such cases, it is difficult to separate by a single distillation column or simple fractionation approach. So what is the solution? Solution is what is called extractive distillation. Extract now, this is, I think, third year students, they are yet to study distillation. Final year students, they may understand this extractive distillation. So here, the solvent used for extraction is phenol. The boiling point of phenol is very high compared to the boiling point of MCH and toluene. It's around 180 degrees, 181.7 to be precise. So what is the dilemma? When we say dilemma in modeling is that you need to be precise. At the same time, you need to have simple model. We say that when model is simple, it may not be very accurate. But if model is too complex, we cannot use it for control. So it's a dilemma, and one need to evaluate the model, or one need to build the model with lot of understanding of the process. Now, if you use first principles model, first principles models, they are differential equations. And therefore they cannot be solved in real time, in real sense, real time. Real sense means within the process control time. You cannot really solve these differential equations, and therefore they cannot be used. Typically, differential equations require integration. So what we need is data-driven model. For process control, we need data-driven model. So we use what is called black box approach. And this black box approach is the name, but it is basically statistics. We are using statistics, and there is same ARIMA model for developing this. So they have used statistical modeling for. Now, in order to test the model, they have not used the real plant, but they have used another modeling technique, modeling software that is called Aspen Dynamics. Aspen Dynamics is a software that can develop dynamic models using first principles. That means what you are doing, instead of having a plant, you are having a plant model with first principles, and you are carrying out the test on that, and then you are using that data in another software called MATLAB, and using MATLAB you build the system, you identify the system. So this is the approach they have taken in order to do this, and lot of students here are there. They can really take such examples. They can build a dynamic model in DWSIM, then carry out the tests like this, they generate a lot of data, and then they can use Scilab in order to build the ARIMA model, or even they can use Python. You can build program in Python to use time series analysis and build the model. So this could be a good exercise which can be published. Then it can be published, and the students, they can add value to their biodata. So it is called multi-input, multi-output system, where we have reflux flow rate and condenser heat duty. Condenser heat duty can be calculated from cooling water flow and cooling water temperature. So using this, you can calculate the condenser heat duty online directly in DCS. And the controlled variables are top product, MCH mole fraction, and bottom product, the toluene mole fraction. So toluene is low boiling point, and MCH is high boiling point material. So in Aspen Dynamics, you capture the process behavior and use the data by carrying out PRBS testing. That is what they have done. This is the paper which is published by the authors which I have given earlier. So they use again PRBS to test and generate the data using the Aspen Dynamics model. They collected almost 500 data points. So you can take a clue from this that you can build a model in DWCM, dynamic model in DWCM, and collect data set, maybe about 500 data set. And you can also have validation data set from the same model, and then run an ARIMA model, identification ARIMA model using Scilab or MATLAB. MATLAB we don't have in the college, so you can use Scilab. And using this, you can build what is called an RMX model, auto-regressive moving average model. Then you can carry out the test on the model. This is typically the box Jenkins method, where you have system dynamics and noise. Use both system dynamics behavior and noise behavior to build a good, robust model. So typical results, what they got is almost, they found that the top product fit is almost 90% in RMX model, not ARIMA model. And bottom product is 90%. While in case of box Jenkins method, the fit is almost 92% in case of bottom product. They also carried out a residual analysis. That means the error, analysis of the error. Error is called residual. You are capturing the information from the model, and what you don't capture is called the residual. It is basically the error. So within 99% confidence limit, they found that the model satisfactorily fits the data. Why you are getting such a high fit? Because it's a theoretical data. It's very simple. We need to understand that the data is a theoretical data. So it doesn't have so much of noise. It has much less noise. But if you take data from the plant, you may end up in a confidence interval of only 75–80%. But that is good enough. And you can keep improving the model as you move forward. So the path in the case of time series analysis is a good system identification for a success in advanced control application. And that good success is possible if you try to extract maximum out of the data which is there, and you are able to predict the error very clear. And you know that the balance is only a noise, balance is only the error because of white noise. So this is the summary of all the entire presentation. So in case of advanced control, the process modeling should be such that it should isolate the system. You don't have to isolate the system completely in order to test it, but you can intelligently take the data out of it and extract the information out of that data by using techniques like ARIMA or time series analysis methods. So this is the conclusion of this particular presentation. So my presentation is over. Now, if you have any questions, we can certainly, I can answer those questions.
Participants, if you have any questions or doubts, please post it in the chat box.
Or they can ask directly also, madam, no problem.
Yeah.
Participant, please ask the question, or you can post in the question and answer slot also.
Sir, I had a doubt regarding the modeling. Can we prepare or construct an AI model which can help us to, to make our design more efficient for a particular operation, like the whole
See,
various
all
components like compressor and piping and all that stuff.
those are basically design models when you're talking about. See, there are different approaches for different objectives. Depending on the objective, you may have to use a different tool. For example, if I am looking for some steady state values, I may use a simulation model and steady state model for predicting the values. But which is basically in terms of hours, and you can run the model for hours and you are not in a hurry. But if the application is for advanced control, we are in a hurry. We have to do everything in seconds. So when you're doing things you want all the prediction in seconds, at that time you have to take a different approach. And that approach is a simplistic approach. You have to take a simplistic approach. Otherwise, you may end up in destabilizing the plant, because the plant would have moved and you have not taken any action, and the plant will go to a different level. You will again predict a different level, so on and so forth. There will be a vicious circle, and you may destabilize the plant. And when we are talking about destabilization of a plant, it is crores of rupees. It is not just ordinary thing. When I destabilize a plant, and if I lose 8 hours of production, I would have lost almost 10 to 20 crores. So it's not that easy. It's very critical. When we are talking about process control, it's a very critical a critical task. And we need to be extremely careful. And we want a very simple model there. And the prediction may not be extremely good, but since we will have again data coming in, we can keep improving the model. So suppose I end up in up to 100 data points slowly, one by one, I may get a model which will be very good. So over a period of time, I may end up in a very good model. And you cannot really make a lot of changes in the plant. That means you cannot make a major step change in the plant. Whenever you do a process control, you have to do very small change, which it is called reversible change. You should make such a change that plant can come back immediately if you need. It can come back to its original state very quickly without taking a lot of time. See, the owners of the plant or the stakeholders of the plant, they will not tolerate if you are going to disturb the plant. So if I sell advanced control project from a company, for example, let's say I have a company and I sell an advanced control project and go to Reliance and start disturbing their delayed cooker, then I'll be thrown out. I will not get beaten probably if I know them well, but I will be thrown out of the plant because they will be losing almost 40 to 50 crores if you lose one shift. So they cannot afford to do that. No. So that is the reason we have to understand the gravity of any action which we take. Now, in case of steady state, there is no problem. You take your own time, you make errors, you recycle, come back again, feed the data again. 200 iterations. Nobody is stopping you because you are sitting in your AC room and keep doing this. So that is not a big issue. So we have to understand what is at stake. So we should understand the stakeholders' concern. That is extremely important. Hello.
Yes, sir, understood. Thank you.
Did I answer you or it was
Yes,
something
sir.
else? Okay.
Yes. Any other questions?
Now, since we have students, I will recommend that you read this book by Box and Jenkins, which is Time Series Analysis by Box and Jenkins. It is very nicely explained how it can be used for process control, how it can be used for financial domain in prediction of stocks and other things, which are not relevant to us. can be relevant to people who enter into stock market.
Yes, I request participants, faculty members, students, if you have any query, please feel free to ask. Okay, so I think there are no queries.
Hmm.
Okay. So, shall we stop here, sir? First of all, I would like to express my sincere gratitude.
Yes, madam.
Yeah, yeah. First of all, I would like to express my sincere gratitudes on behalf of organizing committee for FDP on application of AI in chemical engineering to Iyer sir. I really liked your little Man Ki Baat where you expressed that if the chemical engineering engineers are empowering themselves with the knowledge of AI, they can definitely thrive in their career. So there are huge opportunities coming on the way if they work in, if they grasp the AI. Then sir also emphasized on time series analysis. He discussed about what are the key modeling challenges and real world operational realities. He also discussed about Box Jenkins approach, ARIMA and SARIMA methods, and the importance of balancing model accuracy with simplicity. If model is really very complicated, it won't work nicely. So it was truly enlightening. The case study on data-driven modeling for complex distillation process using Aspen Plus, Aspen Dynamics, and MATLAB provided valuable practical insights. So I'm really thankful, sir. Thank you so much for adding uh, knowledge to us.
Thank you, Manoj.
Again, I would like to thank all the participants and organizing team for having this beautiful session. Thank you again, sir. Thank you so much.
Thank you.
So we are having the session at 6 o'clock again with use of the purchases software for the in research purpose and the routine use. So we will meet at 6 o'clock. Manoj, can you declare again one?
Yeah, so the third session for today, we will start at 6 o'clock. So we will meet again at 6 o'clock. So for now, we are ending the meeting. Thank you, sir.
Sir, I will end the meeting then. Ram, sir.
Okay, yeah.